Hello everyone. Let us today talk about a few very important notions in a topological space which will be handy, throughout the topology or the related concepts you are gonna study in your life. So let me begin with the two notations which I want to introduce. Notation number one, dn. So this should not be confused with d to the power n. I mean the cross product of set d n many times. This is something different. What I'm gonna define. So this is all tuples n tuples where in Rn such that the distance from origin is at most 1. So x1 square plus x2 square plus so on up to where xn square is less than or equal to 1. When I said distance, which distance I am talking about? The Euclidean distance, the usual distance on Rn. Okay, so basically this is bold from here. So if you want to write this kind of thing in LaTeX, so the command is I think slash math bbd. Maybe my slash is the wrong one. It's another side, this or this. So something like that. So let me give you the description of this set in say n equal to 2. So of course I know you know this thing, but still just plot it. So what it is, guys? So let us have this R2 here and the collection of all points. So what is D2? The collection of all two tuples such that their distance from origin is less than or equal to 1. So if it is equal to 1, it would be this unit circle and then this thing. So this is what? This is your D2. So maybe you can sketch it in n equal to say 1 and 3. Of course, beyond that you cannot sketch it, or a human mind cannot visualize it, right? Because it would be the dimension would be bigger than 3, right? The vector space dimension I'm talking about here. If you don't know, in mathematics, there are many kind of dimensions. One such dimension we will be also looking into basic topology called topological dimension. It is due to Lebesgue, if I'm not wrong. We will come to that later on. So another notation which I want to introduce is Sn. So what is this? This is collection of n plus 1 tuple. Note that not n plus 1. In Rn plus 1, there is a reason to denote it by s to the power n rather than s to the power n plus 1. That reason you will encounter when you will be doing something called algebraic topology. So what is it, guys? So this is x1 square plus x2 square plus so on up to xn plus 1 square is equals to 1. So basically, collection of all points in Rn plus 1 whose distance from origin is precisely 1. So say for n equal to 2, what is it? So remember, it should be in R3. So sorry for bad sketch, but something like this, right? Unit sphere. So this is your S2. Fine. Now, so similarly, you can sketch it in for n equal to 0 and 1. Beyond that, the same thing, like in Dn. Okay, good. Now let me begin with the main topic I want to do today. So let us begin with a topological space. Let x tau be a topological space. Let me take a subset and capital A contained in X be any subset. So the concept I'm gonna talk about, you can talk about it for any subset of a topological space. Let me define two sets. Let's say 1 by lambda. Okay. So what it is all U in X such that U is open and U is sitting inside A. So capital lambda is collection of all open subsets of X which are sitting inside our set capital A. Let us have another, say theta. So what I want to define it, say F sitting inside X. What kind of subsets? F is closed and F is closed and A is sitting inside F. I haven't talked about measure theory anywhere, but yeah, I would be giving a link between these concepts in measure theory when I will be giving the lecture series on measure theory. The concept which I'm gonna talk about is related to somewhat, how to approximate sets. I'm not gonna say much about that now. Okay, so let us consider these two sets. Now, note that number one, union U, U in capital lambda is an open set or maybe you can say is an largest open set contained in A. Let us see why. Can you tell me? You may stop the video and think about it. So, guys, this is possible because arbitrary union of open set is open, right? And number two, clearly this is, see, U is sitting inside A for every U in capital lambda. So what it means, union would be there of all such U, right? Another thing, if you take any other open set, let G contained in X be open. Let G contained in X be open. So what you can do is such that G is contained in A. So what you can say here? So this implies G belongs to this family capital lambda, right? So this is natural that G is in union of all such members of lambda, right? So you see, these are the arguments why union U in capital lambda is the. Now I am saying is the. First I have written N. So what you can do, you can cut this and you can write here the. Is the, because it is largest, it is unique. If you take another which is largest contained in A, then both of them would be inside each other and hence the equality holds. So it is the unique. So we can replace N by the or the. So it is the largest open set contained in A. Very nice. Similarly, second, intersection. F in, I think I have defined theta. Let us recall what is theta. Theta is collection of all closed sets in X such that those contains A, containing A. So let us talk about this intersection. And what is it? Is the smallest closed set containing A. Now, this I leave you guys to verify. Up to you guys. Please verify. So these sets are, somewhat special, and you will be understanding as far as we will go why these sets are so special. So let us name them. Okay, let us name them. So have a definition. Definition. Let X tau be a topological space and A is inside X. Then number one, the closure of A is defined to be, so what do we mean by closure of A? Is defined to be smallest closed set in X, of course, containing capital and is denoted by A bar. So A closure, we will read this as A closure. Very nice. The second thing, the second definition, the interior of A. You might have learned this word interior or interior points in your real analysis or metric spaces. Is defined to be the largest open set contained in, sorry for spelling mistake, contained in, I am verbally speaking it fine, in or inside or wholly inside A, and is denoted by A circle. So how we will read it? A interior. So if you see, we have given, specifically the description of these, no? This is what? This is nothing but A interior. This is what? This is nothing but A closure. Now, If you have thought about, I haven't mentioned a thing here. Please, I'm just verbally speaking. Please note that theta and the set theta and the set what capital lambda are precisely non-empty subsets, because if they are empty, we cannot talk about a closure and interior, right? Because this we should have some member in intersection, right? Only then we can talk about such sets. So please make a note of it. So let me conclude it here. That is a closure. What is a closure? It is intersection of all closed sets such that they contain A. Okay. And what is A interior? This is union of all open sets. So these are various ways to write, right? So such that U is sitting inside A. Very nice. Now let us, talk about you know more properties of I mean closure and interior. So let me have it and yeah, I will prove maybe one or two. Then you can uh, you can try other. These are very trivial properties, so don't worry about it much. But these trivial things are, like I said earlier, trivial doesn't mean it will not be, applicable anywhere. It can be applicable at somewhat, very non-trivial, something very non-trivial. So a few properties. So let A comma B be subsets inside X. What is X? X is a topological space. Then let us have properties. So number one, A interior, and again if you take the interior, this is what? A interior. Second thing, if A is sitting inside B, then A interior is sitting inside B interior, as well as A closure is also sitting inside B closure. Similarly here, A closure and the whole closure is also A closure. Okay, third, so if you talk about intersection of interior of two sets, this is precisely the interior of whole. But for closure, only one direction is true. Which one? I forgot. Wait. Yeah, I think yes, this should hold. Yeah. So you should have an example where the other inclusion is not true. Okay, that I'm leaving up to you guys to verify. Now something with unions. So if you talk about this union, this is the union of individual. I mean, the closure of union is the union of closure of individual sets. But this thing is not true in case of interior. So in case of interior, this will hold. Yes. So let me do the second. Rest I am leaving up to you guys to verify, because you have to do these things. Okay. I mean, I should not be the one doing this. And these everything is by definition and the usual set theory. So you should able to do it. So let us verify. Second, please do the rest. without using internet or any Wikipedia. You should or math stack exchange, whatever that thing is. So you should able to do these things on your own. Take time. So second, let A contained in B. We have to show that these things are true. Okay. Now let us understand how we can do this. Now guys, observe that A is contained in B. Okay. And B is always contained in B closure. Why? Because B closure is the what? What kind of set? Smallest closed set containing A. Right. Now, this implies B closure is closed, is a closed set such that B closure contains A. So, but A closure is the smallest, right? Such set. So A closure should be inside B closure. You see, this is, a flawless argument just by definition. And second thing, A interior is sitting inside A, which is sitting inside B. This implies A interior is a open set such that A interior is sitting inside B. What is B interior, guys? It is the largest open set sitting inside B. So this implies A interior is inside B interior. Right? So you say, I mean, these are simple only, somewhat simple. So you can try all others. Those are those will be like followed immediately. So don't worry much about it. So let me have a result. This is something very important. Let X tau again be a topological space. Okay, and A contained in X. So we have given you the definition of A closure, but it's a bit abstract, right? It doesn't directly tells me when a point in X would be member of A closure, right? So let us specify that condition. So X belongs to A closure if and only if for each open set U, of course inside X, such that X belongs to U. Okay, so for every open set U such that X belongs to U, what you should have? U intersection A should be non-empty. Okay, so this is something very, very, very important. You see, it tells you how to check if an element is in closure, right? So let us, sorry, let us do it. Rather than proving this statement, let us write the contrapositive one. So X doesn't belongs to A closure if and only if there exists an open set U in X such that X belongs to U, but U intersection A is what? Empty, right? This would be the equivalent statement. See, the logic is, what is the logic? P implies Q is same as not Q implies not P. So P if and only if Q, it means not P if and only if not Q. Not Q means the negation of the statement Q. This is the logic here. Okay. Let us proceed, say in this direction. So let x doesn't belongs to A closure. Okay. A closure is what, guys? This is closed. It's a closed subset of X. This implies U, let us define U to be X minus A closure. This is what? This is open. Where? Of course in X. Now, U is open. Note that. Also, X belongs to U. Very good. Let us see what is U intersection A closure. Sorry, A. What is it? X minus A closure intersection A. Guys, A is always contained in A closure, right? A closure is the smallest closed set containing A. So this is contained in X minus A closure intersection A closure. Why? A is sitting inside A closure. So you see, this is what? This is empty. So this implies U intersection A is empty and X belongs to U. U is an open set. So you see, we have produced an open set. So we are done this way. The converse one. Let us take this condition. So let U be open in X such that X belongs to U and U intersection A is empty. Let us see what we can get from here. Guys, understand one thing. Let us have Venn diagram. So say U is here and intersection is empty. So A is here. So if you see this area, so this thing, what is this? X minus U. So what we observe here is, note that A is sitting inside X minus U, right? Is it clear? I hope it is. So A is inside X minus U. Yes. Now, let us proceed with our arguments. Note that X minus U is closed. Why? Because U is open. So it is a closed set containing A. Containing A. So this implies X minus U is inside where? Sorry, it is not inside. It should contain A closure. Right? Why? Because A closure is the smallest closed set such that A is contained in A closure. So this is another, right? So it should contain A closure because A closure is smallest. Also, X does not belongs to where? X minus U, right? Because X was in U. So it is not in the bigger set. So and smaller set. So it cannot be in smaller, right? Is it fine? So this implies X does not belongs to A closure because A closure is actually sitting inside X minus U. And we are done. Because if it is in A closure, it would be in X minus U, which will contradict that X is in U. Because if X is in U, it cannot be in complement, right? So you see, this kind of statement we can have about this. About when a point qualifies to be in closure. I want you guys to try one thing. Remark number one, X belongs to a closure if and only if for every neighborhood G contained in X, X belongs to G, or neighborhood of X, we can write small x. Let me edit it. What we should have, G intersection A is non-empty. So you see, please do it. Just use above result and definition of neighborhoods. That's all. That will conclude, or individually prove it. Apply the definition of neighborhood, uh, prove like above. So you can do it. The important thing what I want you guys to try is find a condition Q such that X belongs to A interior if and only if Q is true. So you have to look for this condition. I have directly given you for the closure, but try to see if you have any condition right for the interior. So try it, okay? If you cannot answer this, then I mean there can be many, but you know whatever you know up to now you have to do with that. What you know, open sets, closed set, that's all. And of course topology. So using those ideas, neighborhoods, using those ideas, develop a condition Q, which helps us to see when a point is in interior. Now let me have a few examples. Examples. Number one, let me give you something non-trivial. Let X be an infinite set along with tau suffix COF. I mean, it's a cofinite space. The space with cofinite topology. Okay, consider. Let us consider A contained in X be any infinite set. Okay, what I want is, what is a closure? Okay, let us see. So let X belongs to X be a point, any point, and U contained in X be open such that X belongs to U. You see, I'm using that criteria when a points qualify to be inside a closure. So let us take any point in X and see what's happening. So if X belongs to U, what it means, and note that U is open means X minus U is a finite set, right? It is a finite set. Okay. So what is this, guys? U intersection capital A. Can it be finite? Note that A is an infinite set. right? A is an infinite set, and U is also an infinite set whose complement is finite. So this is also non-empty. Why? Since A is infinite, this will implies A minus this set x minus U. So if you subtract or if you remove the points of this set x minus U from A, this is still infinite, right? Now this is infinite, right? So see clearly this implies that A intersection U is non-empty, right? Because you leave those finitely many points, whatever is remaining, U has. है ना? So that's all. If this is not clear, you can see. So you have taken arbitrary open set which contain the point x, and you have concluded that the intersection of these two sets is non-empty. So what it implies? This implies x belongs to A closure. So you see this A closure is your whole space X. Let me take one more example. I mean, there can be many examples. Let me take one more. Let us consider real line R. Okay, I have already told you what is real line R. So Q means rational numbers. So set of rational numbers. Let us see what is Q closure. Now, for any X in R, okay, and any open set U in R, there exists epsilon bigger than 0 such that X belongs to this thing, X minus epsilon, X plus epsilon, which is inside U. Why? Because that is the metric topology we have, right? The open sets are precisely the set, in how you define in metric space using the concept of interior points. Good. So, and clearly, intersection Q is what? Non-empty. Why this is true, guys? Because of Archimedean principle or property. Archimedean property. Refer Barton, Robert G. Barton. So what you see here is Q closure is also real numbers. Okay, this give me something, you know, like something, a concept of the English word dense. I mean, you see, a forest is dense with trees, right? I mean, plants, trees. Because you see, they like at every, in every neighborhood, you have a tree or plant, right? So that kind of dense, what you have the usual meaning of dense, right? Like our body is dense with cells. Sorry, I'm not into biology. If I have said anything wrong, forgive me. But I think you got the idea what I mean by densities. Sorry, dense. The word dense. So let me formally define it. Definition. A set capital A inside X is called dense if or dense in X if A closure is X. And a simple remark which you can immediately see, because that's what we have used in above examples. Above, I have given you example of dense sets, if you see. So remark, capital A contained in X is dense if and only if every open set U, we have, what we have for every open set U intersection is non-empty. So you see, it is like the set A is kind of, everywhere. So please verify this. If you haven't understood it, verify. Verify it. Write the proper argument like we have done above. So let me conclude with a few more examples. So let us give one more example, because I haven't given you any example of interior. So let us have one. Interior of S1 is what? Empty. Actually, interior of Sn is also empty. One contained in R2. What topology we are taking on R2? The usual Euclidean topology. The topology induced from Euclidean metric. So let me just give you an idea. Or okay, let us take, this is your S1, right? 1, 1, minus 1, minus 1. So you take any point. Note that A interior is always inside A, right? Because A interior is the largest open set contained in A. So if you have to look interior, then you have to take the points on circle. So if you take, sorry, not circle, the set which you are talking about interior. So in this case, circle. So let X belongs to S1 be arbitrary. Similarly, you can do for Sn. So just take this point, say, and take any open set around it. Any open set will contain an open ball, right? So for any open set U such that X belongs to U, what we have? There exists R bigger than 0 such that this X belongs to this ball centered at X of radius R with the Euclidean metric, of course. And this is inside where? U. So now what you do? Join 0, 0 with X. Okay, so you join this line, this thing, and you can extend. Okay, and extend it from 0, 0 via X. So if we extend it, you see, when you, what I'm talking about? Yes. So this is the thing. So what you can observe here is, okay, so this implies take a point Y on, okay, so what I wanted to do, okay, I have to tell you the logic. I have to tell you this answer to this, where it is. Wait, here. So I don't want to tell you answer. So I will, let us write it as something. So cross. So let me stop by this. Find answer for above and complete the argument. Because I haven't told you when a point qualifies to be in interior, right? So that's what I have to use here. So that's why I have stopped for a moment, in between. So let me finally conclude this session, and I want you to guys to refer these two books, or yeah, Topology by Munkris and Elements of Topology by T.B. Singh for more problems regarding closure and interior. See, there can be many associated concepts like perfect sets and all. Um, so you see, there are many things. So I want you to look into those problems, and there are many things associated with closure and interiors. You can see from these books a few problems. Uh, I'm not planning to do everything, so maybe I will do few things when I use them. So for now, I think this is sufficient, and I have already, you know, taken around 50 minutes. So let me stop here. Thank you very much for your patience and attention. I hope this lecture would be little bit beneficial for you. Thank you.